Welcome back to ECE 320. We're in Unit 5, which means you're needing to finish up Chapter 12. There's some supplemental videos using your calculators in a manner that will allow you to quickly compute some of these inverse Laplace transforms. Those are available on D2L. And Homework 5 and Exam 2 are coming up at the end of this unit. In this video, what I want to talk about really is just beginning the process of performing an inverse Laplace transform or setting it up. We want to make sure that what we are partial fraction expanding is a strictly proper transform, which means that the numerator polynomial is of a degree strictly less than the denominator's polynomial order. And we want to determine the roots of the denominator, whether we can fit them into distinct roots or if they are actually repeated roots. Let's establish some notation. In doing the inverse Laplace transform, let's assume that we have a transform capital F of S that's a ratio of polynomials. We might have a numerator polynomial, capital N of S, on top of a denominator polynomial, capital D of S, and I believe in the book they use the notation where the A coefficients are in the numerator and the B coefficients are in the denominator. And we'll try to be consistent, but I may not be. I may sometimes have my A's downstairs and my B's upstairs, so pay attention as we work through this course and this material. But using this particular notation in this video, we now have s to the n for the order of the numerator polynomial and s to the m in the denominator polynomial. And what we want to do is first check those powers. We want to compare the integers n, Nevada, and m, Michigan. If m, the denominator polynomial, is of order bigger than the numerator polynomial, then this transform, capital F of S, is what's called strictly proper, and one can perform a partial fraction expansion directly on capital F of S. This is the order of the denominator, and we are making sure that the order of the denominator is bigger, strictly bigger, than the order of the numerator. And sometimes in future videos, I might have my denominator polynomial of order Nevada in, so pay attention to the notation. Today, in this video, we are having M, Michigan, as the order downstairs, and that's the one we're keying in on. So if our denominator polynomial is of order strictly bigger than the numerator polynomial, then we can just start doing the partial fraction expansions. If, on the other hand, it's not, then we give that transform expression, capital F, a different term. It's improper when the denominator polynomial is less in order than the numerator polynomial. When m is less than n, then f of s is an improper rational function, and we need to now separate capital F of S into a polynomial piece, which we can find using long division, and the piece that we want to perform the partial fraction expansion on, which is a part that we get from long division, which is the remainder term. Our numerator now will be having an order strictly less than the order of the denominator. A couple of facts. A partial fraction expansion can only be performed, and I can't emphasize this enough, on a strictly proper rational function. You'll get nonsense and you'll spend a lot of time if you start doing a partial fraction expansion on a transform that is improper. So first check your orders and make sure your denominator order is bigger than your numerator order. If it's not, then do the division. Once you have the part identified with a strictly proper transform, then the partial fraction expansion of that piece or of that transform is valid for all values of this complex frequency variable s. So we can now plug in different values of s as ways of checking our work halfway through or all the way through our computation of partial fraction expansion. So we can use that second fact that the partial fraction expansion is valid for all values of s, and that could be s approaching infinity. Then we can use that as a check on our work, and sometimes it helps knowing this to find these residues or these partial fraction expansion coefficients. Let's now look at the process, the next step. We're sort of doing a two-stage. One is our transform strictly proper? Not. Then do long division to get a remainder piece that does have a strictly proper transform. Once we have the strictly proper rational function, then we need to look at the denominator and factor it and see if those factors are distinct or simple, or are they repeated. Let's look at the first case where we have distinct simple roots, and these roots could be real or complex and still be simple, meaning we might have a pole at -1, we might have a real pole at -4, we might have complex conjugate poles at -2 plus and minus J3. And the reason we have complex conjugate poles is that gives us then real coefficients in our transform expression. We aren't going to be working with transforms that have complex coefficients. So in that sense, we will be having then roots appearing in complex conjugate pairs. In this particular case, we could then say the associated transfer function or transform is now, let me give myself a little bit more space, is now some polynomial in the numerator, n sub 1 over, and how many poles do we have? We actually, in this example, have 4 distinct or unique poles, where now we're saying that this pole at -2 plus J3 is distinct from -2 minus J3. Those complex numbers are not equal, and so if we associated those with P sub 3 and P sub 4, we would have unique or distinct roots P1, P2, P3, and P4, and we could then look for these residues or partial fraction expansion coefficients, A1 sitting on top of P1, A2 sitting on top of the S plus P sub 2 factor, A sub 3, and A sub 4 sitting on top of S plus 3 factor and S plus 4 factor, respectively. Now, if we do have P sub 3 being associated with -2 plus J3, then in fact A sub 3 will typically be a complex number and A sub 4 will be its conjugate. But once we find or factor the denominator, and if we find that all 4 are distinct, or all 6, however many, then we can find this partial fraction expansion in having this structure. The other case, I'm calling it case 2, is when we have repeated roots. And again, those repeated roots could be real or complex, and this just means that we have roots that are on top of each other. For example, if we had n sub 2 as our numerator, and maybe we had m poles at minus p. So now we would have m roots at s equal minus p. They would be repeated. For example, in the s-plane, if we had 3 roots at s equal minus 2, then we would have the repeated case, and a lot of times I will actually indicate that by sort of moving them away from each other, but in fact, all 3 of those poles are exactly at s equal minus 2. They're stacked on top of each other, and if I drew that accurately, you wouldn't know whether there were 1, 2, or 3 unless I did some other kind of notation, which is why I sort of spread them out a little bit so that you can now see, oh, indeed there are 3 roots at s equal to minus 2. So in this particular case, if we now say we have n sub 2 of s over, what we now have is s plus 2 cubed. Then what we have is we have a1 over s plus 2 plus a sub 2 over s plus 2 squared plus a sub 3 over s plus 2 cubed. So we have to now include this sort of sequence of pole factors that go all the way from first order s plus 2 to the second order s plus 2 squared up to the power of that particular factor, or the number of those roots at that particular repeated pole location. In this example, it was 3, so we would now have s plus 2 raised to the third power. Again, just to drive this home, we need to make sure that we have a strictly proper transfer function in order to do the partial fraction expansion. And once we have the partial fraction expansion, we know it's true for all values of s. Then we need to check to see if we have distinct roots, which allow us to have these simple factors on the right-hand side in our partial fraction expansion, or do we have to now keep track of multiple denominator factors associated with that same pole location, in this example at s equal minus 2. Those are the key issues that you have to be aware of in performing or setting up or beginning the process of performing inverse Laplace transforms.